Да, я думаю, сегодня 20 там мной и с новыми
Он зовет в бар.
Я тебя зову в бар. Привет.
Бар.
Ты куда идешь? Какой в бар? Я не знаю, они пойдут, нет, но я их позвал просто
А кто новый PhD?
Дима и Андрей, которые подо мной. Олаф, а Саня уезжает все еще. Другу не надо. Интересно, я не десю буду или когда десю?
Нет, можно сделать так.
Я знаю девочку. Она тоже снимает мужную пищу.
Да. So you are also yes, I asked already, but you think вопрос, нам нужно 2 раза снимать? Нам нужно 2 раза снимать? Сзади тоже?
Таким углом дурацким.
Исправь.
Some of you again, very few know Rodrigo old times. So Rodrigo was my first PhD student several years ago, but I hadn't known him for much longer. I think, so as a high school student, like 20 years ago, I was an instructor in a high school in Brazil. And later also during his bachelor and during the master we interacted a little bit, but not so much. And then he came to Switzerland and spent some time here. He got his degree from the PFL. And he found a company in Lausanne for 1 year. I forgot that.
I still have that on my CV.
And then after that moved to the US to work with Facebook, where he's been working since 2008. So we all know that Facebook is going to get public soon, I guess. So we need to probably can retire in a very short time. So.
Thank you, Fernando. Thank you all for being here. And this is Fernando gave like a great introduction. There's not much left to say other than so he's been part of most of my computer science education, like since high school. And it was great. Like my degree came from the PFL, but I did more than half of my PhD actually here at the University of Lugano. So I was with the department when it was created, and when we didn't even have a building, a proper building. So Fernando was telling me about the difficulties that you guys now have to fit everybody in this building here. And I still remember the day when this building was open, and everybody was so happy because we were all hiding in different places of the campus. And we could all finally be together, and there was plenty of space for everybody here. So it's great to see. Whoa, must be really tight, really. So it's great to see how much Uzi has grown in the last 4 years, because it's been just 4 years that I've been away, and it's great to see all that. And yeah, so I've been with Facebook since 2008, about 4 years. I've been really happy there. And I've done several things at Facebook. So when I started, my degree was, my master's and PhD education were both in distributed systems. So when I joined, I automatically joined a team that was working heavily on distributed storage systems and fault tolerance. So we have like a huge distributed database there, and it was like a perfect fit for my background. So I was working with a single distributed system that was storing tens of petabytes back then. Now we have like over 100 petabytes stored in this single distributed system. We used to have 1,000 machines. Now we have close to 10,000 machines in this cluster. So it's a massive system, and it was great. Like I worked over a year in this team. I built several things that were related to what I had studied in my master's and PhD. Like I built a massive distributed database replication algorithm for data centers. I built schemas for improved the fault tolerance of this cluster. Several things. actually. And then I realized that in a company like Facebook that is so open and you can really interact with different people in different teams, you profit the best, you get the best out of it if you just move around and you try different things and you learn from them. So I started doing that. So since I started, I've been with 6 different teams, and they're like really different. Like when I left data infrastructure, I joined the team that was building Facebook messages that was released, I think, a couple of years ago. So I joined the first team that was building that feature. I first worked on the back end, but then quickly I realized that there was so much in the front end that I didn't know. I didn't know how it worked. I didn't know how I could build some things like that. So I moved to work on the front end too. So I worked on Facebook chat for almost a year. Like learned a ton of things about like how to build web applications, which are indeed like distributed applications after all. So I learned all that. Then I moved to real-time infrastructure, the infrastructure at Facebook that deals with all real-time notifications that you guys receive in your phones, that you receive on your web page, that you like even chat messages. They go through this real-time infrastructure. And after almost a year, like I've been growing too inside Facebook in my personal career. At some point, I was the lead engineer of this team of 12 people working in real-time infrastructure. And then I realized that I was getting to my comfort zone again. I wasn't learning much. And then I realized it was time for another shift. And then I moved to work on ads and Facebook business pages. So I'm working more on the business side of Facebook now. And I went back to work on the front-end applications. So I've been pretty much all over the place at Facebook. It's been great. And if you guys have any questions about different things that we do there, I probably know like 50% of it. So I would be able to provide you with answers. But please, like, if it's not really related to the talk that I'm giving, like, I would just ask you to defer questions to the end because I'll stay around for a little, just for the sake of the whole presentation flow. And cool. Here is more or less the structure that I'll follow. This is a standard presentation that I've been giving at universities. I'm on vacation, but I really like coming to universities and talking to students. So I took part of my vacation just to go to universities. So I've been to, I don't know, EPFL, then I went to the University of Bremen in Germany, then I went to a PhD workshop in Morocco, then I went to ETH yesterday, and now I'm here. So it's pretty much the same standard presentation that I've been giving. I think it's really insightful and gives a great idea of what the kind of things that we do at Facebook and how our culture is. And you guys give me any feedback that you have by the end, like if you think it's good or bad. So it starts with an introduction about Facebook and I give some numbers on how we have grown and like how big we are. I start always with this, the number of monthly active users that we have. When I joined Facebook, this number was really low compared to what it is now. I think it was under 100 million active users a month. And that is like, for you guys to have an idea, how many of you know what MySpace is? There's still some people that don't know what MySpace is, which is hilarious. Because when I joined Facebook in 2008, our main fight was against MySpace, because MySpace was the #1 social network out there. And so that gives you an idea of how much we have grown in this last 4 years. But now we have 845 million active users. I think actually the latest number that we released a couple of weeks ago was 900 million active users. And these are not accounts. We have billions of accounts created. These are actually users that come to Facebook at least once a month. They log in, they take some actions, they engage with their friends, and they go away or they come back the next day. And in fact, more than half of those users, 500 million, come to Facebook on a daily basis. So in any day, like 24 hours, a 24-hour period, you have over 500 million people that will come, log into Facebook, take some action. Maybe it will be on their mobile phone, maybe it will be on their tablet, maybe it will be on the web, on their desktop. But so this number is massive. And this amount adds to 700 billion minutes spent on Facebook if you sum all the users, all the active users, and in a month. And if you divide that by the number of active users we have, monthly active users, it is about 25 minutes per user per day. So that's how much time like people spend on Facebook on a monthly basis. It's a lot. And if you think like, I think one of the universities that I was presenting this, somebody raised the hand and asked like, do you guys feel guilty about that? And it was, so, and then the thing is like, I usually, when I present this slide, I give a huge like explanation on all the value that we add. But because I wanted to get some technical things on this presentation, I'm trying to skip that. So what this guy triggered was my massive response of like all the value that we added. I'll give you guys just a small snapshot, which is think of all the things that you can do now, that you do now because of Facebook, that 8 years ago you could not do. Think of your family, your friends that you might have like in a different city, in a different state, in a different country, that now you can easily get to share what you're feeling, what you're doing. And like 8 years ago, which is not so much, like even less than that, because 8 years ago was when Facebook was founded, but it was originally just a college network. It was released to the public, I believe, in 2007. So think about like 5 years ago, you couldn't do any of those things that you do now on a daily basis. And you take that for granted. You just do, oh yeah, I'm happy, I'm having lunch. But you should look into it, like how much of that information you wouldn't be able to share with your family if not so long ago, just 5 years ago. So, and think about all the revolutions, all the changes in the whole world that started because of Facebook. Think of the Arabic Spring last year, or think about the FARC revolution in Colombia. Not so long ago, I think it was 3 years ago when Facebook was just started, was just open for the general public. So there was this guy, I like this story, because there was this guy who was really fed up with all the FARC, what the FARC was doing in Colombia. I assume all you guys know what the FARC is, right? It's, these guys, these rebels in Colombia, they fight against the government, they kidnap a lot of people, they are kind of a terror group there. So, so there was this guy that was really fed up with that. So what he did was pretty simple. He created a Facebook page and said like, oh yeah, we are fed up with this, like stop FARC or something like that. And that simple Facebook page started to get some traction, initially in Colombia, but then Colombians, they are not only in Colombia, there is a huge community of Colombians outside. And this started to raise awareness of these people who are outside Colombia, who remember the time when they lived there and how terrified they were of the FARC. And then they got connected with this cause, and they started to join that page, they started to join the movement. And within a few weeks, they had millions in that page, people that came from the same nation, but they were physically separated from each other, but they got together on Facebook for a single cause. And what they did as a result was a massive awareness movement where all of them across the world, they went to the streets to say stop FARC. And they put so much pressure on the FARC that that same year they were forced to release so many of the people that they had kidnapped over the few years before that. So it was a massive thing that started because of Facebook. And you wouldn't be able to do something like that without it. So think about this when you think about this 700 billion minutes in a month. So that was all I told the guy others first. Yeah. So next one. Okay. Think about the technical challenges too. We add 30 billion pieces of content on every month Facebook, like status updates, photos, videos. Every day, more and more people will go and upload more things to their Facebook account. And we have to store all this data. And we have to build systems that will retrieve this data very quickly whenever it's required. So there are many technical challenges that come from that. And it's not only the Facebook the application, it's a platform. It's almost you could say a social operating system for the web. We have this open platform that any developer can build applications that will access our data, that will allow you in their application to connect to your friends on Facebook in a very easy and a very seamless way. And we have, of course, as a technical challenge, we have to support all these developers by building a comprehensive and well-documented API. This all comes kind of from our mission, which is not like to build a web app, to build an application. It's much greater than that. It's just make the world more open and connected. And I think it's pretty strong, and everybody in the company feels that way, that we are doing there is not just building systems, we are changing the world. And it's really great to work in such an environment. Just one graph showing our growth over time. The graph underneath is our growth in terms of users. But one crazy thing is that we are also growing in terms of innovation. In the very beginning, when we had just a few engineers, we would release new features every few months or every year. These days, we are releasing features every week, every month. So it's actually, we push new small features every day to the live website. We push like major features major changes in features every week. And we have new products coming out every month, pretty much. And not one product, like several products coming out every month. Why? Because we believe that as we grow, as we hire more engineers, we should also grow in terms of innovation. We should not like work like big companies that would just try to hire more people to keep what they have. No, we think that if we are growing, we should like provide, we should deliver more too. It's part of this thinking that we have that we are just 1% done. It's like we still have 99% to go, and which is nice. And here it's just a slide showing that this is we strongly believe that social is the next tech revolution. What was browsing in the 90s, when like people all of a sudden could create web pages and you could go to different places in a logical way instead of a physical way. And then what was search in the early 20,000s, where tools were built so that you could easily search the web and find what you were looking for. Now we believe is what social is becoming. It's like a new revolution on tech. Like you see that all new applications that are being developed, that are being launched now, they have some kind of social flavor. They have some social integration. Why? Because that's what the users are asking for now. They know it's possible, so they will force any developer to build applications in a more social way. And we are at the very heart of it, because we are the main social network out there, because we are a platform, because we are a social operating system. And you can see that many industries are being transformed around this new revolution. You'll see that governments are coming to Facebook and having a presence on Facebook, or building applications that have integration with our API. Non-governmental organizations to games. There are companies, game companies that are built around our platform, and they are very successful businesses. Like think about Zynga, a multi-billion-dollar company that was built on top of our API. There's like retail sale, Amazon, Groupon, they have integrations with Facebook. Music, I think the best example is Spotify, which is really strong here in Europe. News too. So the news industry is really going down if they don't adapt. They kind of missed the web train. Now they might miss the social train, but they know it because they missed one. Now they don't want to miss the second one, so they are adapting. They are socializing. They are integrating with Facebook. They are integrating with other social media. So they are trying to adapt because of that. Which brings me to my tech talk. Like, what are the challenges that we have at Facebook Engineering, given all this growth, given our mission, given our where we want to get? And I have some case studies. I told Fernando before the talk that I was trying to go through several examples because I didn't know how technical it could be in this talk. So I think I have 3 case studies. I'm not sure if I'll have time to go through all of them. But the first one is kind of a simple example. I'll try to teach everybody here how a problem was solved over there. And the second one gets more technical into distributed systems. The third one is also distributed systems with a real-time flavor. And so let's see if I can get to all of them. First one has to do with data compression. I told you when I joined Facebook, I was working in this massive distributed database system that was storing tens of petabytes. What I didn't know is that when I joined this team, we were at about 90% capacity on this distributed database. So we are just 10% away of not being able to store any more data. And we were growing at terabytes a day, several terabytes, several new terabytes of data would be added every day, and we couldn't delete all data. And even if we could delete old data, the new data that was coming was more than what we had, like the old data that we had, because every day there was more data coming. So it would just buy us some weeks maybe, but it wouldn't solve the problem. And we were also constrained, physically constrained by the data centers that we had rented in the Silicon Valley. We couldn't just add more racks to the data centers. We couldn't find more data centers to rent because we got all of those that were free. And we could not build a new data center in time. So now we are way more proactive than we were 4 years ago. Like we already have 3-4 data centers in the US that we built. We are building and opening soon a data center in Sweden here in Europe. So we plan the things way better now. But still, our growth now is not as exponential as it was back in 2008. So you can think of like the challenges we had back then. So I joined this team and they had this problem. And the thing is like it only works if you compress. You can only store this much data efficiently if you compress it, right? Nobody will be crazy enough to store all these status updates raw in a raw way in the database. That would be just crazy. You compress the data and then you store it. And the thing is, the algorithm that we were using in this whole system was part of an Apache open source project called Hadoop. And back then, the only compression library that was available was Gzip. And that was the one we were using. Gzip was fast, actually. It was really good. But they had just released a new library for bzip2 compression, which was a little slower, but had 25% more compression rate. And the problem with that library is that it was kind of new, and sometimes it would do something like this. Like, you would take a word like armadillos, you would compress it, decompress it, and it would get garbage at the end. And we didn't know what was going on, like whether the problem was in compression or decompression. It's just that sometimes some files that we passed through the algorithm would just get corrupted in the process. So that, if in a non-deterministic problem, like actually it was deterministic, but it's just that some files would work, some other files would not work, but those that would not work would always not work. So in a problem like this, there's not much that you can do with this library, right? Because you never know that whether the file that you're passing through it will be corrupted or not. So the only way out is like fix the problem with the library or not use it. Not using it would kill us because we were, as I said, 90% capacity. So the option is find the problem and fix it. And I like the way that Facebook works with that. Is that we always try to challenge ourselves. We always try to fix problems that we find on our ways. Let's say the average Facebook engineer would never turn his back to a problem like this. He would just like get down and solve it. And that's what I did actually when I was responsible for this bzip2 compression. And it was supposed to be a very easy task. It was just starting. It was my first month or so. And then I came across this problem, and like everybody around me was very supportive. Like, yeah, you should go and fix it. And everybody knew that, like, with a problem like this, the chances that you actually fix it are quite low. But there was a lot of support that like, I should just try and see what would happen. And meanwhile, we would try to hold on to our capacity as much as we could, like trying to move data to a different data center, or try to get rid of old data more aggressively, or try to reduce the amount of new data that we were creating. But it's a community of trust, and that's what is really great about it. So I'll teach you something about Gzip2. I always feel like when I give a talk, I have to teach something. I think there's a little bit of a professor inside me. And so I'll teach you an algorithm that is at the very heart of Gzip2. It's an algorithm that I came across when I was in college. And it's funny that when I first saw it, it's called the Burrows-Wheeler transform. When I first saw the Burrows-Wheeler transform, I thought, oh, it's funny, it's cool, it's kind of a nice programming challenge, but it looks kind of useless. And I guess by the end of this slide, you guys will probably feel the same. Like, yeah, it's cool, but like, what do you do with that? So the algorithm is a transform. So you take a word, it transforms that word into a different word. And like any useful transform, there has to be a way back. So you take the transform and you can go back to your original data. So I will explain the algorithm by an example. So take the word banana here and putting a circumflex to represent the first letter, and a star, an asterisk, to represent the end of the word. So the first thing you do for the Burroughs-Wheeler transform is to rotate the word in all the possible ways. So you rotate it by taking the first letter, putting it at the back, like this, and you do it again, 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 until you're done. No, there's one more. Again, and then if you rotate one more, you go back to your original word. So these are all the possible rotations of this word. Everybody with me?
Yes.
Okay, cool. Now you have, what you have here is a rotation, it's nice, but then you sort all these words. Think of these lines as different words. Now you sort all of them. Sure, that's what you get. So now you have banana, a banan. So these are first because they start with A. So these words are all lexicographically sorted. All with me? Cool. So now the cool thing about the transform is that it takes one of the columns in this matrix, and that's the transform. But if you take the first column, it doesn't have a lot of information in it. It's just all the letters of the word sorted. That's like which information you would have on it that would allow you to reconstruct the original word. No, because you just sorted everything. But if you take the last column, that has a lot of extra information. It's not clear at the first sight, but you can reconstruct the word if you take this column. And that's the transform. So the Burroughs-Wheeler transform for banana would be BNN, like circumflex, AAA. In fact, you don't need the circumflex and the star, so AAA would be together. Now the quiz. I hope you guys are all with me. I'll ask you to tell me how to start with this word and get back to banana. So again, we have the last column. Now, how do we rebuild the matrix? So is there any other column that I can build from the last one?
You can sort it, so you're going to get the first column.
That's a good one. That's a good start. So if I sort them, I know that the first column is just all the words, all the letters sorted. So I have the first column. Now what do I do? No pressure. It's there.
So checking the last and the first, you know which is the first letter?
The last and the first, what you're saying is that because of the rotations, the last and the first are connected?
Yeah, I mean, you start with the static string symbol, and you check the corresponding character, and you know the first letter of the word.
That's a good one, and actually you can generalize, right? You know that because these are rotations, you know that B is always before the A, you know that N is always before the A, you know that the other N is always before the N. So if you take the last column and you move it here, you have all the pairs, correct? And if you have all the pairs and you sort them, you have the first and the second column, correct? That's what you do. Now, how do you build the third column?
Same again?
The same thing again. So you take the last column, you move to the front, then you have all the three letter sequences. Then you sort them again, and you have the first three columns. And you do it again, 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 and that's it. Now how do you find the original word? The circumflex, right? We know that the word starts with the circumflex. That's why we put the circumflex and the star. So the word that starts with the circumflex and ends with the star is the right one. We pick that. That's it. As simple as that. Very nice algorithm. A lot of fun. Why the heck do we need to learn this at school? I'll tell you why. It has to do with this. If you do the Burroughs-Wheeler transform, if you have the same pattern happening again and again in a word, like banana, you have an, what ends up happening after the Burroughs-Wheeler transform is that the same letters will be grouped together. they'll be grouped in chunks of like repetitions of the same letter. Like it happened here. You have B alone, you have the two M's together, you have the three A's together. And what is that used? Like what's that useful for? I'll give you a hint. It has to do with compression. So if you have all the letters that are the same grouped together, so you can compress that in a more efficient way, right? You just have one letter and then a counter of how many times it happens in the sequence, and then you can review the original sequence. You have much better compression that way. So that's why the Bruegel transform is used on Gzip 2. It's at the very heart of Gzip 2. And that's what gives the Gzip 2 algorithm the 25% extra compared to other to things like Gzip. And yeah. The problem that we had at Facebook was that, well, after some debugging, and I managed to isolate the problem with a test case, is that our BWT algorithm was broken. And that's the funny story, like how this library was broken. I did some investigation actually when I was looking into this. And the library was imported from another Apache project called, this was Hadoop again. So it was imported from the project called Ant. So you guys, anyone knows what Ant is? The make for Java thing? Okay, so it was imported by Ant. So I went after that and trying to find what the Ant guys did to fix this bug. And I discovered that the bug was not fixed at the end. And in fact, it was an open Jira, an open ticket for 7 years. So it's just that the guy that took the library from Ant didn't check that the library was actually not deprecated, but not in use because it was broken, and everybody in Ant knew that it was broken. And that's why it ended up in the Hadoop project. And with Ant, the funny thing is that the guys, they just stopped using this library. They went back to another library that was like 10 times slower. But for them, it was okay because it was just like compressing small files during the compilation time, and not always. So for them, performance wasn't an issue. But using a 10 times slower library for us was out of question. Gzip 2 by itself was already slow. And the reason is like why it was open for 7 years. It's because it was taken for the Ant library. It was not built for Ant. It was taken from another library that was originally C++. So the guys from Ant, what they did is that they took all the C++ library and they did a semi-automatic translation. Well, which means they ran a script that did most of the translation from C++ to Java, and then they solved the bugs by hand. Like whatever was broken, they were there. It's like, oh, okay, I fixed this, I fixed that, I fixed this, I fixed that. So if you do that, you end up with a library that nobody knows how to debug, right? The guy who did the semi-automatic translation didn't know about the code that he was changing. The guy who wrote the original library wrote it in C++ with meaningful variables, like counter 1, counter 2, whatever. And the code in Java was semi-automatic, so the variables didn't have much sense out of them. So that's why the library was so broken, and it was open, like the bug was open for over 7 years. And nobody knew how to fix it. The thing is, like, as we really like a challenge, again, the solution is not like turn your back to it and try to find something else. It's like, okay, I think I can deal with this. I think I can solve this problem. And so, because I already knew the Bruegel linear transform, I kind of had a head start on debugging this. And so I did some debugging on, like, I understood what the library was doing. I took some, well, I got to a point where I could understand what the semi-automatically translated code was doing. And I got lucky, I guess. And I got to this line of Java code that looked a little suspicious because there were fors before and after this one, and all of the fors they had an extra plus one. This one didn't have, and actually that was the problem. And so yeah, so that was the fix, simple fix. Solved a 7-year-old bug and saved us a lot of money back then, and allowed us to actually scale our systems a little bit more and like get to the point where we could build infrastructure in a faster way. I think this is shows an example. It doesn't like I didn't use much of my specific background in distributed systems here. I used a lot of my background in algorithms though. And it looks simple, like to explain the Bruce Willis transform this way that I did, but believe me, debugging several thousand lines of code semi-automatically translated in Java is not that easy. But anyway, it shows how much impact you could have in an environment like the one we have at Facebook Engineering. And like, it shows how much trust we put in even new engineers that are just starting. And like other companies might just oversee or try to babysit them too much. At Facebook, we just treat them as other engineers, and we trust them and we give responsibilities. And now let's get more to the meat of fault tolerance in distributed systems. Something that you always hear in class for distributed systems, that if you're working with, like, I heard that all my life, if you're working with thousands of machines, there's only one thing that you can trust, that failures will happen and you have to tolerate them. Every fault tolerance class will start with something like this. And I actually, well, with thousands of machines in running the systems that we were building, actually I had the opportunity to see that in real life. So actually, it is true. Like, if you have thousands of machines running the same system, there's only one thing that you can know for sure: that failures will happen, and it will happen very often. Like, on a daily basis in our data center running our Hadoop cluster, we would have like 1 or 2 failures on average, and that's on a daily basis. The day after, there would be 2 more failures, and you have to tolerate them. Your system has to continue running despite those failures. And it's really important to do that if the data that you are storing is valuable, like the pictures of your lifetime, the connections with your friends, the meaningful things of your life, which is exactly what we start Facebook. And if you have this valuable data stored on a single machine, how do you make sure that you don't lose that data? What can you do? Like, let's say you have just one database storing what was Facebook 8 years ago, just with the Harvard University. What would you do to, like, tolerate failures of that machine?
Pray hard.
Pray hard. That's a good one. Yeah. I tried that. It didn't work for me. These are easy questions. You guys can just say the easy answers to them.
Hardware replication.
You replicate the data, yes, pretty much. Well, where are you? Okay, wrong one. So you just replicate the data, right? You had A, now you have 3 copies of data A. Then if one of them fails, you have a copy of it. I believe everyone in computer science knows that, because we do that with our backups and all that. And so, pretty easy, right? You know, the problem with this is that you get redundancy, you get fault tolerance, but you are storing 3 times more data. Remember what I just mentioned of our capacity being close to 90%? That problem didn't go away with just Gzip 2, because Gzip 2 gave us 25% more space, but our data was growing continuously every day, like more data would come, and we would have to store it. So we had to find other ways to compress this data, other ways to store this data in a more efficient way, to not waste the capacity that we have. And that's the main problem that I tackled on this project. And to get to it, before I get to it, I'll just explain the software stack that we have at Facebook. And this is for our what we call data infrastructure team. It's a team that I first joined. If you remember in the beginning of the talk, I mentioned I joined this team of systems, distributed storage. And the data we store is not the user data, it's not online data that's accessed online. Is log data, which is way more than the user data. It's data that comes from our web servers on a daily basis, on an hourly basis actually, with activity on our website. How much time it took for a page to load, which links were clicked, debug logs, anything. Like all those logs, they get aggregated and they are stored in this massive distributed database. And, well, which is amazing because, I'll get to that. So this is a stack of this system, the system that stores, the distributed database that stores all of these logs, all of this information. Like over 100 petabytes of information is stored in this database. It starts with the servers, and every server is running a data storage unit. So this is, you can think of it as a daemon that runs on each server. And all it does is like receives a block to write, and receives requests to read the block, and returns the block as a response to that read request. As simple as that. All it knows is that I run on this machine, I read blocks, I write blocks. On top of that, we have a Hadoop distributed file system. That gives an interface of a file system on top of this data storage units. So on top of the Hadoop distributed file system, what you can do is like write a file, read a file, read this part of this file. And internally, what HDFS, which is what HDFS does is it breaks this file into blocks and stores these blocks into these machines. As easy as that. So on top of HDFS, you have files. And these are massive, these are usually massive files. Files with hundreds of gigabytes of data. Files with terabytes of data. And you also have Hadoop MapReduce, because even if you have a system that distributes the file for you, if you want to process one of these files, you cannot rely on a single machine, because that would just be too slow. Have you ever tried to read in a single machine, in a single process, like 100 gigabytes of data from this? It just takes a lot of time. And the system we have in place, which is, again, part of Hadoop, is Hadoop MapReduce. What it does is, similar to the data storage units, it has data execution, or task execution units running in each one of the servers. And whenever you want to, let's say, process one of these files, you write your task in terms of map and reduce steps. The map step will take every record of your file and translate it into a key and a value. So it will read a line, like get some semantic value of this line, and build a key and a value. So all you have to do in MapReduce is write a program, like two programs. The first is the mapper. What it does is like, given a line in my file, assume these are text files, and they all have like 3 different lines. Given a line of my file, I should create a key and a value. That's the mapper. So after I'm done with the mapping phase, there's a reduce phase that takes all the records that have the same key and pass them to a reducer. The reducer receives a key and a set of values, like all the values that were mapped to that same key. So that's how you build a MapReduce task. And you build that very simple, centralized kind of program, but it will be executed in a distributed fashion. So the task execution units, what they will do is that they will run mappers and reducers on those files. The file will be broken in blocks. Each block will run the mapper. You can easily see that if you have mappers that will just take lines and break them into keys and values, you can run the mappers separately for each different block of your file. So that will just parallelize well. And the reducers are kind of centralized, but still, like for records of the same key, they can run on different machines. So it's going to be distributed in that way. You just have to make sure that you're not mapping all your records to the same key. So this is a nice way to build distributed systems in a framework like this, but it's still too hard for someone that doesn't have the background in computer science that we all have. For example, data scientists that we have at Facebook, they look at this data that we store and they try to extract meaning out of it. And so, but they don't know how to code as well as we do. So what they do, or what we did for them, was to build a query engine and a database layer on top of MapReduce and HDFS. This is the Hive project that was born at Facebook. And it pretty much offers a SQL interface on top of all this distributed framework so that users can create tables instead of files. They can run SQL statements on these files instead of creating MapReduce jobs. And it's all like compiled and run in real time. So you write your SQL statement, you send it to Hive. It will be translated into a MapReduce job, and what you get back is just a file with a table with the result of your SQL statement. And on top of that, we have a graphical SQL interface to help users that don't even know SQL build SQL to run this queries. It's a pretty complex stack, and we were a team of, let's say, when I started, 15, 20 people, and we were building like all this stack from bottom to the top. And yeah, this is just a summary of what I repeated several times already. Like we stored tens of petabytes of data. Now it's close, like it's over 100 petabytes. Files with hundreds of gigabytes and valuable data that cannot be lost, and constantly under storage capacity pressure. And now we'll get to the original problem that I said, that replication is just using too much capacity. If you have a file, so going back to HDFS, the way HDFS provides fault tolerance is every block of a file will be replicated 3 times. So you take a file, a big file, let's say, that is broken into blocks A, B, C. What you end up storing in the data storage units are 9 blocks. 3 blocks for A, 3 blocks for B, 3 blocks for C. You all good? Mm-hmm. Cool. And replication is good for 2 things. One is fault tolerance, the other is performance. Fault tolerance because if you lose one replica, you have other replicas to read from. Performance because if you have some piece of data that is too hot, like too many people are reading from it, if you have it stored in a single machine, that might become a bottleneck for your system. So you replicate that, now you can read from different machines. Then you release this tracker. But for us, it was mostly for fault tolerance. So we looked at this problem, we looked at this, this system, and we were trying to find ways to keep our fault tolerance level, but reduce the amount of space that we were using. And there are some algorithms in fault tolerance that they're very good for the fault tolerance part, but they are not very good for the performance part. And these are erasure codes. I don't know how many of you guys have heard of it before. Erasure codes? Yep, yep, yep. Do you guys know, have you guys heard about parity bits in memory? Like you create a parity bit so that if you lose one bit, you can use that parity bit to recover the data. That's the erasure code. Like it's just that there are some other codes that use more than a single parity bit. And you might use like 2, 3, 4 parity bits. So that if you lose any 2, 3, 4 bits on your original piece of data, you can rebuild that piece of data with your parity bits. Good? So, yeah. The thing is, systems like ours would not use erasure codes only because the performance of them is just too expensive. If you lose one block, let's say we are using erasure codes, which means for every bit of the blocks, we build this parity bits, and we end up building a parity block. And you lose one of the blocks in our file. To rebuild that block, we would have to run an XOR on all the other blocks of the file, plus the parity block, to recreate the original block and then start reading from it. It's just too expensive. So you cannot rely only on the erasure codes for that. Our solution here was to build a system on top of HDFS that would provide a hybrid approach, like a mix of replication and erasure codes. And that's what we did. We would use like replication for performance in terms of if you lose one block, let's say you lose only one machine, and there are some blocks in that machine that you lose. We still have replication, which means that we can quickly recover that data from a different machine. But if you lose 2 machines, then we would resort to something like erasure code. I think this is better explained with an example. So the beginning is pretty much the same, like how this algorithm would work. Then you have the file on HDFS, and this file has 3 blocks, A, B, C. Originally, in HDFS, this file would be replicated 3 times. So every block would be replicated 3 times. You have 3 copies of A, 3 copies of A, 3 copies of B, 3 of C. What our system would do, and think of it as a system on top of HDFS, not running together with HDFS. That's kind of a better way for us to build this without changing the core of Hadoop, MapReduce, and HDFS systems. So what it would do is like, look at this file and see, oh, this is using too much capacity. Let's run the HDFS RAID, that's the name we gave to the system, algorithm. So what it would do is like, first, create a parity block. Parity block, very simple, I just gave you guys a hint. Take the first bit of A, do an XOR with the first bit of B, an XOR with the first bit of C. That gives you the first bit of your parity block. Do that for all the other bits in these blocks. You get the parity block in the whole. So you create this parity block, and you replicate this parity block. They have 2 copies of it. Okay? Think of this as an append to your file, like it's the last block of your file. Good? Now, you have more fault tolerance, right? Because we just added these parity blocks here, so that if we lose one of those blocks, we can use this block plus the others to recover it, right? If we lose all the replicas of A, we can take B, run an XOR with C, and an XOR with ABC, and we get A back. Good? We have more redundancy. We have more fault tolerance. Now, what can we do in terms of reducing the amount of replication here and keep the same level of fault tolerance? One would easily say like, oh, just get rid of one replica. Good. Now, I ask you, is this system as reliable as the previous one? So the previous one would cope with the failure of any 2 machines. What about this one? How many machines can fail? 2? 2 for sure, yes. So if I lose all the blocks that have A, I use B, C, and ABC, and I get A back. Good? Now, is it all I can do? Like, what if I lose 3 machines? Will I lose any data? No, because it's going to be, in the worst case, it's going to be 2 machines of the same block, plus 1 machine of the other block, any other block. So I still have 1 copy left. So this system has less storage, because now instead of 9, I have only 8 machines, and it's more reliable than the previous one. So we ended up saving space and increasing the reliability of our system, of our distributed system by doing this. And yeah, I just explained everything that is in this slide. I can go forward. Okay. Yeah. I'll probably just go quickly through this one. It has to do with real-time infrastructure. I'll just skim through it. I don't think I'll get into the big problem that we'll solve. But yeah, I want to explain some things to you guys on how we build our real-time infrastructure. What this infrastructure what it does is deliver real-time notifications to all the Facebook users. Everyone, all the Facebook users, you guys, when you receive a push notification on your phone, when you receive a chat message, when you receive a notification on the website that something happened, it went through this piece of infrastructure. And this problem is solved in a very simple way. It's just like, I'm Facebook, you guys are clients that are connected to me. All I have to do is deliver to you guys a stream of data. It's like, here is your notification number 1. Here's your notification number 2. Here's your notification number 3. So I have to deliver a consistent stream of data to you guys. And then you receive these notifications in order. And now the problem happens because of the 3-tier architecture that is used on. The problem becomes hard because of the 3-tier architecture that is used for web services or websites in general. So this is how websites are built. It's oversimplified, but it's kind of a general picture of what happens. You have the user, that's you at home using your laptop or your your desktop. And they connect to Facebook via web server. Like they connect to a web server that they send HTTP requests, reads and writes. And this web server stores the data or reads the data and writes the data to a database. Now, the nice thing about this architecture is that all the data, all the state of your system is stored in a database. And because you're doing that, you make the web server completely stateless. All it has is application logic. It's a code that you wrote that runs the web server. And this allows you to replicate the web server. They have like several copies. And that's how websites scale. So on Facebook, we have, I believe, 5,000 or 10,000 actually. I lost track of the number of web servers that we have. Might be even more than that. And when a user wants to send, let's say, a read or a write, it can now connect to any web server. So you just send a request to one of them, and you get a response, and then subsequent requests will probably hit different web servers if you have as many as we have. So you are never hitting the same server. So in this environment, how can you provide a consistent stream of notifications to your clients? It's just hard, because there's no way a web server, because of network security and how HTTP works, there's no way a web server can contact the user directly and say, oh, here's notification number 5, here's notification number 6. All requests, they have to come from the user and then get a response from one of our web servers. And no web server here has data, so they will always have to resort to some other tier to get the next value in your sequence. And if you store all that on a database, then you're going to kill our database, because this is just too much data. Only chat messages, it's more than 10 billion a day, I believe, plus notifications, I would say that would double it, like 20 billion a day. So if you are storing this stream of notifications in a database, you're just killing our performance. So there has to be another way. And this is just what I said. And that's how we solve the problem. By adding an extra tier. This tier we call, it's a channel server. And what it does, it's a stable connection from Facebook to a user. And it's like a specific, you can think of it as a specific machine that will store only your message queue, only your stream of messages. And you still have your web servers here. These are all replicated, like we have tons of them. You still have your databases there. The channel server stores all its data in memory, so it's less expensive than a database. And you have only one channel server per user. Of course, one channel server will serve several users, but one channel server per user. No, no, that's right. One channel server per user, not one user per channel server. But you have several users per channel server. So let's say, and this was an easy way to map you to it. Your channel server would be your ID number. So you take your ID, mod the number of channel servers, and you hit that channel server. That's the guy that has your queue. And as simple as that. There's some level of some very rudimentary fault tolerance being built at the channel server level. But the way we do at Facebook is like the way we used to do actually. Things have changed a little. Is we would have clusters of 3 or 5 channel servers that would be tied together on the same rack, on the same data center, very close to each other. And they would be constantly monitoring each other. So they would operate as a single machine, but more reliable, so that if one fails, the other would easily take over all the channels that were stored on that machine. So very rudimentary kind of fault tolerance that was being implemented. Other than that, so you can simplify these partitions, we call them partitions, as a single server, but it's a more fault-tolerant server. And go back to what I just said, like how to map a user to its channel server. And I just mentioned it could be as easy as taking your ID and doing a mod operator, and skip this one. Doing a mod operator and getting to that channel server, and you would probably think, oh, that's so stupid. Like a company like this as big as Facebook would never do something like that. So until 2 years ago, that was exactly what we did. So the way we would map a user to a channel server is take the user ID, we would mod the number of partitions, that's the more reliable channel servers, and we would hit that partition. As crazy as it sounds, like actually this is scaled to hundreds of millions of users, billions of messages. But it got to a point that it was just unbearable anymore. Imagine that we are running out of capacity and we have to add more channel servers. You add more channel servers, you're changing that formula there, right? Everybody will get remapped to a different channel server. You put the whole system down, and then you have to bring the whole system up again. And that's exactly what we did. So it was crazy. But then we have to fix this problem, right? And then we built a system for dynamically switching channel servers from one to the other one. I will skip the details. I'll just give you guys an idea of how the protocol would work. The user is originally connected to one channel server. And by the way, I skipped something that is kind of funny, but it's like I mentioned that there's no way that a web server would contact the user to submit these notifications, right? But I just mentioned that, yeah, well, a channel server would solve this problem, blah, 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 and you guys don't want it. So we still have the same problem. It's HTTP. The requests, they have to come from the user to the web servers. How do you make that the user is not constantly sending HTTP requests to the channel server? So it turns out we do something called long poll. So the user makes a request, we hold the answer, and then as soon as there is a message, we send the response back. That kind of simulates a notification being sent from the channel server back to the user. So it's kind of a hacky way to implement notifications coming from a web server to the user. And okay, that's how it works. So you are connected to one channel server, and we store the mapping from users to channel servers in a database. So this information rarely changes, only when we add new machines, when we are doing maintenance. So it's okay it doesn't hurt performance if you store it there. So we update this information and we tell the new channel server to prepare. Like, okay, prepare because you're going to receive a new chunk of users, and you're going to be responsible for them. We update the cache in all the web servers. So there's a local cache running off them that stores this mapping from users to channel servers. Because remember, notifications, they are born in our application logic, and that's the PHP code. So they're born here, and then the PHP code will have to update the queue of the user that is receiving that notification to say, oh, here's a new message, right? So these guys, they all have caches of this mapping for performance. And we update all these caches. And we tell the old channel to disconnect. And we tell the client to reconnect. The client gets the information about the right channel server from the web servers. And reconnects. Sounds easy. It's a very complicated system. And more interesting than that is that it was all built by an intern during 3 months that he was at Facebook. And it was a pretty cool project. Like he had a major impact on the way we do things. He improved a lot the quality of the service that we were providing. And he did all that in 3 months, and he was a second-year bachelor's degree student. Which is really cool. Here are the challenges. And I just wanted to mention other projects. I focused a lot on the things that I worked on because those are the ones that I know the most. But we pretty much cover all the domains of computer science these days. We have distributed systems, databases, operating systems, people working on Linux kernel or network interfaces. Security, we have a strong team of security experts. Programming languages, we have our own PHP compiler. Our PHP, people make fun of us because we use PHP, but our PHP resembles today a mix of Java and Python. So it has several features that we imported from Java and several features that we imported from Python. And that's the PHP that we write code on. And because we have this compiler that we built on our own. We have computer architecture teams. We built our own data centers. We built our own machines. So there's a big team of engineers that they optimize the hardware that we have in our data centers. Teams working on search, machine learning. Our search problem is different from web search because part of our information is already indexed. And different than that, like a lot of the web search is kind of direct keyword search. You have a keyword, the search engine has a mapping keywords to websites. It kind of does an intersection of all the keywords that it did. Like here's the list of websites for you. In our case, most of our search is like graph search. What are the friends of your friends of your friends that were born in the 70s and live in this city? This kind of statistical search. These are the kind of problems that we have to solve internally at Facebook to build the features that we built. To recommend the people that would be with a high probability, the people that we know. When we go to Facebook and we have this list of people that you might know. So yeah, we have to find those guys. Data mining, machine learning. If you like interfaces or software engineering, we have a strong platform team, internationalization teams, and many, many more. Like every week, I know about a new team or a new research area that we are working on. I have a few slides about our culture. I think I still have 1 minute before going out. Let's do this fast. So it's a hacker culture, but not in the way that you would think like a hacker that tries to steal your password or something like that. It's hacker in the sense of prototyping. So
because
we
they
try.
already have it.
What?
Because they already have it.
Yeah.
The password? I don't think we actually store the password. It's an MD5 hash of your password.
Yeah, I mean, you have people's lives.
That's
old-fashioned.
we don't need the password. That's what
Exactly.
Well, that's because you trust us. Anyway, so it's a prototyping culture. So we try to prototype things really fast. Like have the smallest version that you can build of the new feature that you are responsible for out as soon as possible, and then you iterate on top of that. And that's the way we do things. We don't, like if you are building, let's say, Facebook messages, the way we build it, like we got the first version out as soon as we could, and then we iterated on top of it. We improved other things. And that's how we do everything at Facebook. And not only in engineering, like other departments too. And these are posters that we have all over the company to remind us of these values. Move fast and break things. Like don't be afraid to try different alternatives to your problem. Like break things is not go and break your chair or break a system or break a computer. It's break norms, break paradigms. Other things. What would you do if you were not afraid? Like, don't be afraid to take risks. Because I think the most valuable outcomes, they come from big risks that you take. So you shouldn't be afraid to take them. And you learn from that. So I guess we all learn more when we make mistakes than when we get something right. If you get something right, it's because you already knew that. Or maybe you didn't know you knew that, but you knew that. But if you make a mistake, hardly you'll make that same mistake again, because you learn something from it. And that's part of our values too. Like if you fail, like just fail harder and learn from it. And the last one, proceed and be bold. And that's one of our core values. Like proceed and be bold and try to take risks and make a difference. And this all works because we work in small teams. All the projects that I mentioned, they were really small teams. The first one, the simple Gzip 2 thing, it was just me. The second one, it was led by me and another engineer, and we had one more guy working on it. The third one, on the real-time infrastructure, it was my intern and me working on that. And that's how, it doesn't mean that we are a company of individuals. No, we are a company of, we have teams and we are very friendly with each other and we learn a lot from each other. I have freedom to go to any team, any person in the company, talk to them and learn from them. And we do that a lot. I recently had to make some changes in some parts of the code that I didn't know about. I went to the team that worked on that, and 3 or 4 guys stopped everything they were doing, took me to a room, and they taught me everything about that system so that I could build what I needed to build. We are very friendly with that, but we just believe that if you want to get something fast something out fast, then you got to work in small teams. Here are some examples. The photos application was built by 1 engineer initially, video by 2 engineers. The PHP compiler, the first team had 2 engineers on it. The Facebook for iPhone, 1 engineer. And the open compute servers and data centers, the project that built our machines in our data centers, was originally designed by 3 engineers, and during a conversation over lunch, so I think the first version of the design of the machines, they wrote in a piece of napkin. We have hackathons to foster innovation in the company every month or so. For 24 hours, we stop everything we are doing and we do something completely different. It doesn't have to do, and that's across the company, not only engineering. And it doesn't have to be, if you're an engineer, it doesn't have to be an engineering project. I know of some engineers that once built a suspended garden in our backyard for their hackathon. It's something for you to express your creativity. And like several projects were born out of hackathons as a result of like expressing your creativity during those 24 hours. Video was one of them, like uploading videos to Facebook. Chat, mentions, the PHP compiler, many more. We have bootcamp when you start at Facebook. During the first 6 weeks, you work with several teams of your choice. You're not assigned directly to a team. You pick the team that you want to work on. And you pick that as a conscious decision after having worked with them and other teams. So during the first 6 weeks, you are exposed to the code base. You can make changes from day 1 in any part of Facebook. And you pick some teams that you like, and you start working with them for those weeks. You solve tasks for them, interact with the team, and the team that you feel like there's the strongest match, that's the one you join. It's a great thing to do. Yeah, we have hackathons like every year or year and a half. You can switch teams for a month. That's pretty much what hackathon is. You choose, every team will have hackathon projects. You choose a team, you choose a project. You can go work with them for a month. And by the end of this month, if you are happy with that and you want to stay on that team, you just stay there. If you feel like, no, I'm better off where I was before, just go back to your own team and no hard feelings happen like at all. That was one of the ways I switched teams once. Like, it's a very common thing to do that all the time. And then when I was working on real-time infrastructure, I was pretty happy there, but I felt like, well, it doesn't feel like I'm learning anything, you know. And then there was a chance for a hackathon, and I felt like, okay, I'll go out for a month, and then I come back here, and I continue to work there and there. And I was not thinking of staying with ads and pages. Like, it just didn't feel like I would stay there. But after a month working with those guys, there were so many things that I learned, so many things that I still had to learn, that I just couldn't see myself going back to my old team and like continuing the same plateau that I was. And yeah, that's hackathons. And okay, there's several social perks. Like, we are an open work environment. There are no walls. You can talk to anybody. Mark Zuckerberg sits among the engineers, and you can go and talk to him if you want to. We have excellent food, like social events, high quality speakers that come all the time. Nobel Prizers, Turing Awards, like President Obama went there, former President George W. Bush went there, celebrities. We have several benefits, transportation benefits to take you from anywhere in the Bay Area to work. We have laundry on site. You take your dirty clothes to Facebook, we wash and we fold them and we give them back to you. We have on-site gym and like several other things. Really, I don't use all of them. Yeah, if you are interested, like as I mentioned in the beginning, like we always say that our journey is 1% complete. So we still have 99% to go. That's reflected in several aspects. If you go to the Facebook headquarters, you see that you can see the columns and you can see the roof. Like, we actually doesn't have a roof, so you can see the isolation, and it looks kind of raw. And you would think like, gee, the Sun left this place in a horrible condition. It was the headquarters of Sun before, and then we bought and we moved in. And you would think that Sun was the one who left the place in that condition, but no, like, that was the first thing we did when we got there. Like, just break the roof, take out some walls, leave the columns exposed, because we want everybody to feel that we still have a lot to build, a lot to do in that company. And yeah, and if you're interested that we have internship opportunities, those are like 12-week internships. You have a mentor. The projects are all interesting and challenging. The third one that I mentioned was a project of one of my interns. And I can tell you, like, all the projects there are like that. We don't want an intern to go back home and just ditch their project and not use it. We want all the projects from all our interns to run into production or to be used by our employees. And yeah, there are tons of benefits for interns, more than for employees. I think we pay for everything, for the visa, for the trip, for housing. We give a bike, we reimburse for luggage that they take back home and whatnot. And by the end of the internship, every intern is already evaluated for a full-time position. So if they did a good job, they receive an offer to stay or to come back after they graduate. Or if there was any problem with their internship, we give them a feedback and like lessons that they can learn before they apply again to Facebook. It's a very clear process. Very transparent. And we also have full-time opportunities if you're interested. I talked about bootcamp. I talked about some problems that we solve. I gave an idea of the culture that we have. It's more like a startup culture. And yeah, I think the biggest advantage of Facebook is like the people that you work with over there. I learned so much because of my colleagues. And I feel like I had something to teach them too. I'm pretty sure I have taught some of my coworkers some lessons that I learned through life before I joined Facebook. And yeah, it's a very nice learning environment. And yeah, if you're interested, here's the website, facebook.com/careers. If you have any questions about this presentation, about Facebook or anything, feel free to send me an email. I have some cards if you want to. And yeah, if you have any questions, feel free to go ahead and ask them.
So one or two questions from the audience. If there are any. Okay.
How did your PhD degree help you with employment, Facebook? I mean, not in relationship with your experience which you made during your PhD study. I mean, you worked with Hadoop, but you could work with Hadoop in any commercial company in the industry and then go to Facebook. And does it give to you some additional benefits, like in Intel, it's some bonuses in terms of salary if you have PhD degree, for instance, or in IBM?
So I could have worked on other companies too. I got offers from other companies. So why I chose Facebook? It was the best match in terms of culture.
No. I mean, how did your PhD degree help you, or
get there, or stay there?
Well, help you to get in. Why you didn't go to Facebook right after university without making PhD? Why you decided to make PhD and then go to Facebook? I mean,
well, if I wanted to join Facebook when I finished college, I couldn't because there was no Facebook back then.
Ah, okay.
That's one thing. I graduated in 2001 from college, and Facebook started in 2004. 2004, I was already in my second year of my PhD, and yeah. But I see your question. Like, you could say, why didn't you join Google right out of college?
Yeah. Just what's the use?
And I think I just wasn't. I didn't know exactly what I wanted to do when I finished college. I had the impression that I would like to become a professor and be a researcher and go to a research lab, and that's what I did out of college. So some of my friends actually went directly to the industry, but I did not. It was a personal choice. And it turned out the way it turned out. Like I think I had so many great experiences during my master's and my PhD. I went to several conferences, I published several papers, and by the end of it, I kind of felt like I wanted to try something different, like to really have an industry experience and see how systems are built. And maybe a few years from now, I'll just think of doing something different again and maybe go back to academia or whatnot. But
okay, so you don't think that PhD was a waste of time? Because when my friends in
Oh, it
Google
was
told me
definitely
like
not.
it's waste of time, why you go out from industry, blah blah blah. So I just question people from industry. I mean,
I learned a lot on my PhD,
Okay.
that's for sure. And some of the knowledge that I acquired during my PhD, I actually used at Facebook. And for example, I worked on database replication during my PhD, and I built a data center, a multi-data center database replication algorithm. And I believe the background that I had from my PhD helped me a lot in building that system. And there are several things that come up all the time. I worked a lot on an algorithm called Paxos, and at some point we were using Zookeeper that has a version of Paxos running in it, so I knew how it worked. And I think now we are building some systems using an operating that is close to Paxos, so it really helps, but the choice of joining Facebook after my PhD was just personal.
okay, well,
But it's not a...
what's about your personal experience? Just about your personal opinion.
From what I can tell you is that from my friends that went directly from college to the industry, depending on the company that you go to, you just reach this learning plateau that you just don't learn anymore because the company just doesn't foster innovation and learning.
Yeah.
And then if you didn't do all the learning that you needed during your university time, during your bachelor's, master's, and PhD, then you just